Today's guest is Sukrit Ranjan. He is a theoretical astrophysicist by training and a planetary scientist by trade. Sukrit Ranjan's work is focused on the origin of life on Earth, the search for life on other worlds, and the atmospheres of rocky exoplanets. From Beyond Media, I'm Felix Tuchinski, and this is Humanity and Beyond. All right, so how are you doing today, sir?
I'm doing great, Felix. How are you?
Fairly well. Busy, but it's life. So I want to get started right away and ask that there was a minor planet that you got to name in high school. Am I saying? Correct me if I'm wrong.
It was named after me.
Oh, named after you. So how did that come about? What was the what were the circumstances of that situation?
I was a finalist in a science competition for high school students, the Intel Science Talent Search. It's relatively well known in the U.S., and the finalists all get minor planets named after them.
So what work did you do because I assume if it was was it some sort of competition or?
Sure. Are you talking about the current work, the phosphine on Venus work, or the earlier high school work?
Oh, I was just trying to get some context for leading into your current work today. Trying to see if there was some sort of a connection. Of course, but yeah.
The connection is that I think planets are cool. That's all that's going on. That earlier work was very unrelated. It was clouds on Mars.
I understood. My apologies. Yeah, let's jump right into the Venus stuff then. I understand there was observations of Venus using the James Clerk Maxwell telescope back in 2017 and 2019. So obviously we weren't looking for phosphine then. Do you have any knowledge as to why we were looking at Venus at the time?
Sure. So the observations were led by Dr. Jane Greaves in the United Kingdom. Jane actually was looking for phosphine. She didn't particularly expect to find it. She expected to more test the instrument and to set upper limits, but she was also conscious in the back of her mind, I think, that phosphine was produced by life on Earth. So she was kind of excited that, what if we see it? And she was very, to my understanding of the way she's told us, she was very shocked when she did in fact see it. So she did, of course, the thing any responsible scientist should do, which is she went and she applied for time on a bigger, more sophisticated facility to kind of verify and double check the observation, and also to use it, a different geographical location at a different time to try to eliminate some of the things that might be spoofing a signal. And she detected it there as well. She and her colleagues subjected it to a bunch of tests, and they found that it seemed to persist as a signal. And so they came forward and to our team, and we started trying to figure out, well, if it's really there, what might it be?
And apparently there have been, I'm not sure if this is even a rumor. I'd like you to confirm or deny my suspicions, that there was apparently a phosphine reading from an old probe we'd sent back a couple decades ago. Was it that the data was overlooked, or that it just wasn't recognized as a phosphine signal, or do you have no idea what I'm talking about?
I do actually know what you're talking about. I actually was speaking with some of the team responsible for that report earlier today. So I think you're referring to a really interesting paper that came out at the beginning of the week, analyzing data from, I believe, the Pioneer spacecraft, which sent a couple of descent modules through the Venusian atmosphere. On the descent modules were a variety of instrument packages, including what is essentially a mass spectrometer, which is an instrument which is used to try to measure what are the components of the atmosphere. And what this team did after they re-reported that, well, we think we found phosphine on Venus, is they said, well, can we see evidence of this claim detection of phosphine in this mass spec descent data? And so essentially what happened is they looked through these very old measurements, and they did in fact find that in the middle of the atmosphere, they were finding signals that were indicative of the presence of phosphine. Now, this is not a slam dunk measurement. It is in situ, which is great, but it's not a slam dunk because there are other things that could spoof the signal as well. For example, H2S, the presence of H2S. But they did a couple of tests involving different isotopes of the molecules, and based on those isotopic tests, they feel that the most conservative explanation for their data is the presence of phosphine on Venus as well. Now, you asked why wasn't this looked at? Why wasn't this detected earlier? We asked them the same question, and I don't think anyone really knows, because I don't think any of us were in the room when those decisions were made. But based on what they've been able to glean together and what they communicated to me, so this is a little bit of hearsay, the folks who are working on that original mission were extremely conservative and extremely careful. And one of the things they really didn't want to be wrong, and they really wanted to be very robust. And the other thing they wanted to do is they had their priorities. They were kind of focused on a few certain specific chemical species. So one of the things they tried to do was, if they saw a molecule in some parts of the atmosphere but not others, they deprioritized it because they're like, well, maybe the instrument was just acting up when it passed through that part of the atmosphere. And they were also not really focused on phosphine and molecules like that. They were particularly focused on the isotopes of the noble gases, for what I can tell you about certain other processes. So the thing about phosphine, though, is you don't expect it to be present everywhere in the atmosphere. You really only do expect to find it at significant concentrations in kind of the middle lower part of the atmosphere, where it's protected from being destroyed by any of the many processes which destroy it. There's a whole bunch of data that were just basically never processed and never looked at in detail. And so they're trying to go through that process and figure out what they can figure out.
Gotcha. Is there any process that we just don't know of that could be occurring on Venus to generate this phosphine?
Absolutely. So one of the things I love about what you've done in this interview so far is you've elucidated that there's two important, interesting things about this discovery. One is that there's phosphine on Venus, period. And that's a claim that needs to be scrutinized on its own as well. And other folks who need to go analyze the data and need to take under instrument measurements and so on and so forth. So we can't really depend on that first. We need to, it's worthy, that claim is itself worthy of scrutiny. The second part of the claim, the one that my team and I'm more responsible for, is the claim that phosphine on Venus is particularly weird. And that in particular, we haven't been able to figure out a mechanism that we are aware of, like volcanism and lightning and stuff like that, that can produce the requisite amount of phosphine on Venus. I really like the other point you brought up, which is that, well, maybe there's some other kind of mechanism. And that's really a possibility. That's not just a fig leaf that, oh, maybe there's something we don't know about. There's a lot we don't know about Venus. It's an understudied planet. In particular, its lower atmosphere is really hard to probe with probes and facilities, because if you send a probe there or a mission there, it tends to melt. That's not really great for collecting measurements. So there could be a lot going on in the lower atmosphere of Venus we just don't know about. Similarly, there's a lot about the photochemistry and the chemistry in general of phosphine that we don't know about. A lot of the relevant rate constants, a lot of the relevant measurements of how quickly it reacts and how fast it reacts simply isn't known. Not for any fundamental physical reason, there just wasn't a good reason to study it before. One of the things we hope is that our work will motivate follow work on both of these areas. And it may well be that when we look into this in more depth and we improve our understanding of phosphine and of Venus, we might well discover some kind of abiotic mechanism that can synthesize this, perhaps related to the cloud droplets.
Cloud droplets, in terms of like, would it be a different molecule, or would it just be like solid phosphine, or?
It's not solid in the sense that most of what we've simulated but not all of what we've simulated is gas phase chemistry, because we seem to be detecting phosphine in a gas form. However, phosphine is detected at a layer of the Venusian atmosphere coincident with clouds. Clouds are made up of droplets of, in this case, sulfuric acid and water. One of the questions that we have is that there might be some kind of exotic chemistry going on in these solutions that we don't know about, which might be generating phosphine. We've looked at the obvious candidates, but that's just the obvious candidates. There might well be something we don't know about.
One of the candidates that you couldn't rule out entirely is, whether you agree with it or not, is the possibility that it could be biogenically generated.
Yeah, that's one of the options that we have not yet ruled out. So we might yet rule it out, or someone else might yet rule it out, is the prospect of some kind of biological production mechanism. Yeah, that is not ruled out yet. I really like the way you're saying that. A lot of times people just want to jump straight to the potential, to the biogenic interpretation, and that should always be the hypothesis of last resort.
It's also a matter of magnitude, like orders of magnitude. Like, let me phrase it differently. There's processes that would be an order of magnitude more likely than life. Am I correct in stating that, or is that even too hard and too vague to tell at this point?
What I would say is that philosophically, we always have to consider life as a hypothesis of last resort. Whether life is more or less likely than other options is hard to quantify. All we can try to do is we can quantify the other mechanisms that are capable of producing pH3. Lots of things are capable of producing pH3. The question is, can they produce enough pH3 to explain the signal that we see, which is a concentration of 20 parts per billion. And so far, the mechanisms that we've evaluated so far, according to the calculations we've done, aren't able to explain that, aren't able to produce it at a high enough rate to explain the signal that we see. They fall short by many factors of 10, what we call orders of magnitude.
And another hypothesis is that it's caused by volcanic activity. What would be the known process that would cause phosphine to come from volcanoes? Because I don't normally on Earth I don't associate phosphorus and volcanoes in my mind, or maybe I'm just not educated enough on the matter.
Yeah, that's another really great point. So volcanoes do put out phosphorus-containing species, but the lavas on Earth are relatively what's called oxidizing. They have a lot of oxygen in them. And the phosphorus tends to come out for the most part in the form of molecules like phosphate, which is a P connected to four O's, four oxygens. It does produce also a certain amount of phosphine, but it tends to produce very, very little of that molecule because the lavas here on Earth tend to produce mostly the oxidized forms, more oxidized forms. On Venus, the default assumption, although it is not yet constrained by measurements, is that we expect the lavas on Venus to produce even more oxidized species of P. But even if you don't make that assumption, if you just assume lavas that are like Earth or even significantly more lower oxygen than the Earth lavas, you still can't produce enough. According to our calculations, it doesn't produce enough phosphine to explain the signal we see. It would have to be about 7 orders of magnitude. So that's 10 to the 7 times more reduced, has 10 to the times more H less O relative to Earth-like magmas for it to be able to explain the signal that we are seeing, or at least that's what our calculation suggests.
That's a heck of a lot less. Wow.
Yeah, but again, there are big uncertainties here. What I want to emphasize is that we're doing our best guess and we're trying to use the scarce data we have. And so the shortfall is quite large, but it might just be that someone comes along and does a really clever measurement or sends a probe and shows that, hey, actually, no, you're wrong. Some of these volcanoes are weird. They're weirder than we could ever imagine. And you could have some super weird volcanoes that are putting out a ton of phosphine. That's something that we don't expect, but we can go and measure and check that possibility.
We'll be right back. We just want to thank all our listeners, and especially our supporters. Without you, all this would not be possible. The absolute best way you can help us is by sharing us on social media. If you really like what we are doing, you can support us on Patreon. That's patreon.com/humanityandbeyond. So this is a hypothetical question. If you were to, if NASA or ESA or just any space organization has at least put out a statement that they might reconsider sending a probe to Venus or move up their timetables for, this understudied planet, as you put it. If there's a room for an instrument to be put, and your team is given the go-ahead to design the instrument to look for this phosphine. We've touched on it a little bit, but what would be your best case? You'd be like, okay, well, we want to remove life as a hypothesis completely. What would be a way to do that? Just to completely just move life out of the media's head, just to silence them on that point, I should say.
Yeah, I don't think I want to silence or empower anyone. I think the science is the science, and we should just see where the evidence takes us one way or the other.
Of course.
I think one class of measurement that has the potential of really clarifying the debate is if we could somehow put an instrument there that could directly measure the composition of the part of the atmosphere where we report the presence of phosphine, and in particular try to measure the concentrations of different phosphorus-bearing species. For example, in addition to phosphine, so the first and most fundamental thing would be by going there in person to confirm whether or not phosphine is really there. That's step one. But after that, you can say, well, how much phosphine is there, and how does that compare to the amount of phosphate, which is again that P connected to 4 O's, the fully oxidized form. How about phosphite, P connected to 3 O's, and other forms of phosphorus? The reason this is interesting is then you can start to build up a picture, and you can start to ask, is it only phosphine there that's present? That would be super weird. We don't really expect that. We expect it to be mostly phosphate. But if that was the case, it would tell us something. Similarly, if we can get the precise concentrations for all these other molecules, we can start building models and saying, well, if we model chemistry as we know it, what parameters do we have to tweak to reproduce these ratios? And if we reproduce those ratios, maybe that'll give us a hint as to what might be synthesizing it in the clouds of Venus, if it's there.
Are there any other places in our solar system with unexplained levels of phosphine? Or I'll expand the question to say any unexplained levels of anything, period, like any element. That is a particularly interesting case.
This is a great question and answer. There's so many unexplained things in our solar system that, I wouldn't be able to say. There's all sorts of unexplained things that I don't know about. In terms of things that are particularly kind of noteworthy, when you just make you tickle the possibility in the back of your head, not at the front of your head, of maybe life. In addition to phosphine, they've now searched for phosphine on Venus. The Russians have with their or the Russians have, I believe, and they've reported that it's not there. But what is there on Mars, or what's reported to be there, it's debated on Mars, is methane. And the presence of methane is also kind of interesting because we don't, that's not also something that we expect to be present over geological time. Now, I should emphasize that the detection of methane on Mars is highly disputed. There's actual disputes there's disputes at all levels on lander measurements, on telescopic measurements, and so on and so forth about whether methane is there on Mars. And even if it's there, now people have come up with abiotic mechanisms that weren't obvious early on to explain its presence. But no one has yet confirmed it. No one has really drilled down and been like, okay, this is no one has really proved there's methane on Mars and this is what's putting it there. So I think that's another really interesting area of debate and interesting of study to look into.
So no Martian cows for now. Understood.
Not unless you play that game Terraforming Mars, in which case lots of Martian cows.
Lots of Martian cows. All right. And my last question for you was, I understand, did you receive a certificate in Origin of Life Studies?
Yeah, at my PhD institution, Harvard, they've become very interested in Origin of Life, and one of the interesting programs they offer is a little bit of formal training in that discipline, the research that's being done and the current ideas that are being explored. So yeah, I did the first certificate in origin studies over there.
Or Origin of Life in terms of like 3.5 billion years ago, Origin of Life like Origin of Life in exoplanets and stuff?
Both. I'm really interested in both. I'm really actually interested in, one of the main reasons I'm interested in the search for life on exoplanets is the opportunity it offers to test theories of, potential opportunity it offers to test theories of the origin of life. In the sense that we do a lot of really great work here on Earth in the lab, but there's always that pushback that, oh, your laboratory conditions aren't a realistic simulation of early Earth. Oh, you would have had this or that would have frustrated this pathway you found, or oh, this mechanism can't really work. And you always have the counter argument that, well, early Earth, you have a planet's worth of surface area and millions to billions of years worth of time. You just can't simulate that in the lab. Well, if you can look for life on other planets, and particularly planets orbiting other stars, that gives you dozens to hundreds of laboratories that have carried out this test of trying to form life just like ours. And if you can read the results of those experiments, maybe you can learn something about theories of the origin of life.
Oh, so the holy grail for you would not just be to find an Earth-like planet, but an Earth-like planet that is very new, like maybe just a couple 100 million years old.
Any world that has, so first off, young planets are really interesting, particularly ones that don't have life, because then those are potential windows into our own Earth, into getting an understanding of what our own young planet was like, which is remarkably hard to do. But it's also interesting, I'd be happy to find any planet. I think the most exciting thing would be to find a planet that we could confirm is habitable, that life as we know it could exist on, and then to either find or not find life there. Because either of those tells us something about how easy or how hard it is to get life started.
Understood. All right. Yeah, that's all my questions. Is there anything that you would like to emphasize, specify, or just talk about in general? The floor is yours.
Well, first, I'd like to just thank you for the very skeptical, calm attitude you have towards this discovery. It's important to be really skeptical in science and to let the scientific process happen. So we've put our best foot forward. We've tried to make our data public and put all of our methods publicly as well. And we look forward to the process of replication and independent analyses. And I think it's really good for that process to happen unimpeded with full freedom. And I think that's a really important thing to me. I also really like the not being sensationalist about this and keeping extremal ideas like the presence of life to be in the background, not the first hypothesis. And I think that's a really good approach.
My personal philosophy is that there's already enough sensationalist media. I don't need to be another voice in that chorus.
Yeah, I think self-skepticism is a challenging thing to do, and being careful is a challenging thing, but it's, I think, what we all hope to strive for, I think.